Rathod sir, I have sent you a brief about in the chat box itself. Okay, you can use
Okay.
that, sir.
Okay.
Yeah, hi Shiv, good morning. Uh, should we start?
Yes, sir, we will start now. So
Yeah,
let
sure.
me, just. So, welcome you all for this second day of STTP. And I'm happy that all of you have, and most of you actually have submitted the quiz on Moodle. And those who have not submitted, or if you have any, we will sort it out today if there is any login issue. But majority of you have actually completed the assessment for yesterday session. And today, and happy that us, not three, but actually four people from Multiple, and there is our Damodara, and I am to introduce. Damodara is a decided technologies based out of Bangalore. He's primarily responsible for application engineering and consultation for customers across India from defense, aerospace, and corporate sector. Prior to joining Enterprise Technologies, he was with as a product manager. At IEEE, he was contributing as an industry liaison to semiconductor industry. He was actively involved in IEEE Standards Association activities, supporting system Verilog, and he supported a new learning initiative from IEEE Blended Learning Program, received appreciation award from IEEE President for his contribution for proliferation of standards and learning activities. Damodara carries 17 years of industry experience with core expertise in front-end design and verification, board system design with experience in telecom equipment, medical systems, aerospace, automation, and automotive hardware system design. Throughout his career, he supported educational and competency building activities. He contributed in developing learning solutions in the space of design, verification, timing analysis, system design, and more as a subject matter expert. He received appreciation award for his contribution in the competency building initiatives for internal engineering technologies. Currently, he is supporting IEEE in education activities. He is actively assisting Electronic Sector Skill Council of India (ESSCI) in developing National Skill Qualification Framework (NSQF) for engineering job profiles in VLSI domain that include design and verification engineer, system design, in VLSI, and embedded system specialization for Vishwesvaraya Technological University, Karnataka, and Bachelor of Engineering in Electronics and Communication stream from Bangalore University. So, welcome you. Thank you very much for accepting our invitation, and we are looking forward for your thoughts on VLSI design. Sir, welcome, sir.
Thanks, Ratan, sir. Thanks for your introduction.
Yeah.
So, on behalf of S.P.I.T and Untitled Technologies, we welcome all the participants for the STTP day 2 of the STTP program. So as per the agenda, okay, today and tomorrow we are going to be taking you through the intricacies of modeling combinational logic circuits and sequential logic circuits in our sessions. So, and the sessions is going to be driven jointly by me and as well as Mr. Shioppa, who is with us, okay, right? And our team members Avinash also, okay, and Harish. So we are going to address the typical challenges what you come across, okay, when it comes to modeling combinational logic circuits and sequential logic circuits from the HDL fundamentals to begin with. And then we'll also run you through some of the typical constructs. Okay, generally what we have seen is that when you are using the constructs of Verilog Hdl, generally you expect the constructs to behave in a certain way based upon the way you are modeling. For example, if you take if-else loop, or else if you take a case construct, or else even the non-blocking and blocking assignment statements, you expect them to behave in a certain way. So as a result, what happens is that whether you are intending something and are you really implementing the same way. That means if you are implementing a multiplexer, the question is that are you choosing the right construct to implement a multiplexer? And at the same time, if you are inferring a state machine with n number of states, then is the control logic is only running through those states, or they are actually spilling over to other unwanted states also? So like this. So there are numerous scenarios of this nature you basically go through. As a result, what is important for you is that to understand how these things really work and why they play a very, very critical role. Remember, these guidelines, what we are going to be talking about today and tomorrow, they are very important for you in modeling of any type of digital system which you are going to be working at. And at the same time, it is also important for you to understand that the guidelines, it is equally important in ASIC design flow and as well as FPGA design flow. So don't be under an impression that we are talking about the ASIC design flow and the guidelines is very much relevant only for the ASIC design flow. Not really. It is equally relevant in case of FPGA designs also. So as we proceed further, Shilpa and the rest of our team will also run you through lot of those details, okay, right, with the relevant examples also. And plus, we are also going to be providing you the tool access, because any training program, it is incomplete without we dirtying our hands. So hence, at Entuple Technologies, we are giving all of you an opportunity, right, where you can not only learn through the case studies and the examples what we are going to be sharing in our sessions. If you want to practice those things, we know that during this isolation, every one of you would love to run through those case studies with the help of the tools on your own, not just seeing through the demonstrations. You also want to run through those things. And in fact, in this program, what we have jointly come up with Rathod sir, we are giving you that provision also. So how the mechanism works: once if you complete the live sessions in the evening hours, right, you can take up the tool access. So you can subscribe for the tool access with a very, very nominal fee of 750 rupees, where you can take up the sessions tool access, where you will get 16 hours of tool access from our end. So our team will share you the link how you can subscribe for the tool access. So those of you are willing and those of you are very keen to have the lab sessions, okay, on your own. Remember, this basically allows you to run through the cadence tools from your home itself. And it is also, and since majority of you are also faculty members, it is also an opportunity for you to understand how a practicing engineer works in the industry, even sitting in this isolation, or generally when engineers they get connected to, from their work from home, how they work with their enterprise networks. So you will get to understand those things. And plus, you will also get exposure to the Linux complete management, okay, in the tool access and everything in a very systematic manner. And thanks to our networking infrastructure team, so we have brought in such type of facility. And for your information, in the last 6 months, nearly more than 5,000 plus engineers in India and across the globe, they have taken this facility, and it has really made a difference to their learning and as well as for their work activities also. So we are bringing that same facility for all of you. So just don't feel like you can completing the online sessions. Beyond that, you can also work through the lab sessions remotely on your own. wherein you also get technical support from our technical support team during those hours. So we request all of you that take the benefit of that, and that is going to really benefit you big time. And if in case if you have any issues, you can always contact our team at cadence_support@ntupl.com. So we'll help you with that. So in the course of today's session, okay, right, our team will share you that link also, how you can subscribe for the tool access. Those of you are keen, so please take the benefit of them. So benefit of that facility, so that the program can really serve the benefit for all of you. And now I would request Rathod sir to introduce our another speaker, Shivappa, also, so that we can proceed with the rest of the session. Rathod sir, should I do the
Yes,
honor?
yeah. I'll introduce, no problems. So, Shiva is the Director, Excel VLSI Technologies. He carries 24 years of industry experience in the field of VLSI. He has industry majors like Wipro, SmartPlay, Mindtree, and recent at various capacities like Project Manager, Delivery Manager, Senior Vice President, Operations. He has served major clients like Intel, Texas Instruments, and more across geographies like India, US, Europe, and many more. At present, he is driving Excel VLSI Design Services team. So welcome, sir. Welcome, Shivappa, sir. I welcome to this STTP and internet to our college.
Thanks, Surendra sir, for giving this opportunity. So hopefully, your team will get benefited out of these 2-day session on design verification using Verilog. Thanks, Damodar, as well for bringing me to this course. So, is my voice clear? Can I get started with the session?
Yes, yes, sure. Yes, sure.
Yes,
Just
clear. Please.
one question. Yesterday, I understand that there were a couple of sessions. I couldn't attend all of them. Was there an introduction about ASIC flow, FPGA flow? Should I directly get started with Verilog, or should I go through the ASIC flow as well?
Sir, basically, most of the faculty members, almost all, they are from VLSI design background.
Okay.
So you can directly go ahead.
Yeah, Shiv, I would request you to skip to the agenda, okay, right, of this. Okay, directly we can get started with modeling of combinatorial logic circuits and sequential logic circuits. Sure.
Okay. Oh, okay, sure. So we'll align accordingly.
Rathod sir, can you give presenter access to Shivappa, please?
Yeah. Visible to everyone?
Yes, sir. Visible. Yes, sir. Visible, audible. Everything is clear. Go ahead.
Okay. So we'll get started with Hdl modeling. We'll understand a little bit background about the Hdls available and used in the industry and different modeling types. And also we'll get started with Verilog program structure. And further, we will learn more about the constructs, what we use for modeling, combinatorial and then sequential circuits. Okay. So, as you all know, right, in the beginning, the designs which the industry was using was having fewer number of gates, right? At that time, it was kind of, rigging up some circuit and then making things work. So that was the initial stages of hardware design, where the complexity was very less actually. So as the time passes, right, the designs grew larger and more complex, and then they started looking at the gate level models describing, right, you need some assistance of a language. Of course, at that time, there were other languages emerging for the software, like C and other languages, higher level languages, rather, I would put it that way. So of course, the hardware industry also felt to address the complexity, there is a need of a language. But of course, higher level languages, whichever were available at that time, so they were not directly usable, right? So that's where I'm talking about now, the complexity of gates, number of gates in order to describe a particular design, a particular circuit, a logic circuit, right? It grew over a period of time, and where the order of number of gates for a circuit, started increasing exponentially. Okay. Now, what was the thought? Now, can I use the language in order to describe whole design at an abstract level? Okay, so what is abstract? I mean, is at a summary level. At a summary level, can I describe using a language? So this is the design which I wanted to, bring up. And can I describe using a language at a higher level? So that is the thought process. So this is a simple ALU design. This instruction memory and the register file ALU, data memory, control logic, which today you are all right. You are studying, right, the basics of microprocessor, microcontroller, right? So now that led to the complexity, and the need to address this complexity led to the origin of HDL. So how HDL can help this hardware description language, right? Hardware to describe the hardware, we use a language, right? And it allowed designers to talk about what hardware does without actually designing hardware, right? So you're telling the language, describing using the language, this is what is the hardware I want to implement, right? And it also helped to discriminate or separate the behavior from the implementation of the functionality. So implementation, I mean here, the actual circuit which you make using gates, right? That is the implementation part. But before you get there, the behavior at a summary level, at an abstract level, using HDL, you could describe just like any other language. Using a program, you could describe. So that's the behavior part of it. So that's what in the ASIC flow, we start with the architecture and then the design, then whatever you come up with, the block diagram what I showed, you are going to code, you're going to use Verilog program to describe that hardware. That's where the Verilog part, or Verilog or VHDL, that is HDL part, comes into picture. So there are two HDLs predominantly used in the industry over the years, Verilog and VHDL. These are hardware description languages. So they are used for describing concurrent behavior of hardware. Little bit, if you look at this word concurrent in the hardware, there is nothing called sequence, right? In the software, you execute, you write C program line by line, you execute and you expect the output, right, at each stage. But how do you compare the same in the hardware? But you are using a language to describe the behavior, but how do you visualize the hardware components which are there in the chip, the logic, the gates which are there in the chip, right, to work sequentially, right? So basically, now of course, based on the logic, you may say, talk about the sequential circuits. Every clock, a process or the sampling and the driving happens, but we're talking about hardware which is having concurrent accesses. For example, now this particular, if I say it's a flip-flop, this flip-flop, if this is the input to this flip-flop and then this is the clock, and then every clock, this need to be sampling the data and then passing it to the output, right? So, and similarly, this flip-flop. Now, all are concurrent. Concurrent means parallel, also you can visualize, right? So, how you can describe the behavior of the hardware or the concurrent processing of the hardware using HDL. So you also, one more difference with respect to higher level language, you can also visualize this is a structure or a platform or it is static, right? The hardware is static, but based on the inputs, it behaves in certain way how you have designed the logic. Okay. So that also brings into the structural modeling, right? The static or the structural modeling. So what is structure? Basically, we are putting an array of gates and the flip-flops in order to make the hardware, right? And now the using HDLs, you can also describe the structural way. Okay. Behavioral modeling for procedural and sequential, like I said, here the sequential or the behavior, every clock, right, it has to do something, right? That is what we model using the procedural constructs or the sequential constructs. So we little bit talk about it more in detail. I'll describe the differences between these modeling techniques. Okay. Of course, HDLs are used for developing stimulus generator and checkers at large for verification. Now, you have this, let us say this is the design, and now you want to verify. You want to verify, typically in the industry, we use a structure called Testbench in order to drive the inputs and collect the outputs and then check. So this is output collector and then checker, and then this is bench driver, right? What it drives is stimulus. We call what is stimulus? Basically, the inputs are driven, right, as per how this device has to behave in the system, right? Based on that, you are driving the inputs and you are collecting the outputs and then comparing whether you are getting the desired outputs, right? So you can relate any of the devices available today. For example, you can take a microprocessor, what you have studied, what are the inputs and outputs it has. For example, now 808586, if you take, so of course the clock and reset could be the inputs, and other side you will have address is an output, right? Either 8-bit or 16-bit, and the data in and data out, right? So data in is input data, data out is output data, and there will be some control signals to say whether it is write or read, right? And this could be now this if you imagine microprocessor and this is memory. Now you are this checker has to behave like a memory, and now this processor has to whatever it drives and then need to collect the address and the data and save, and then when it processor does the read transaction, then it has to give back the data, right? That's how you can visualize this test bench part, okay? The checkers and the test bench part. This is for verification. So all that I'm saying is HDLs, support for this hardware modeling and writing test benches, the verification. That's where, in the ASIC flow you would have studied what is verification. Verification is about applying the test vectors or the stimulus to the design and collecting the outputs and checking against the standard behavior expected results actually. HDLs are also used to represent synthesized netlist. What is synthesis? Synthesis is about converting RTL to RTL, register transfer logic, to gate structure. So now the gate structure, the gate level netlist, we call this netlist. Netlist means list of nets connecting the various hardware components. Those are gates and flip-flops, right? And so you can write out the netlist in Vhdl or Verilog. Okay. So basically, if you look at the high level block, you can visualize in the form of the block diagram, right? The next level of details, what processor block would have, and then further this block diagram, after synthesis, you convert into gates, and then each gate is made up of transistors, right? And these transistors are the ones which you fabricate on the chip in order to realize the complete chip, complete ASIC, okay? The application specific integrated circuit. Okay. Are you able to relate what I'm talking, and is the flow okay?
Yes. Go ahead.
So now, like I was mentioning about, you can always any questions, anything you may have, you can post it in the chat box. I'll just take a pause at the logical conclusion of my topic, and then I'll answer your questions, if anything, if you're not able to follow. Okay. So I was mentioning about the software, higher level language and software programming language. So now to understand, always questions comes, why one more language was required, right? And there was always some tweaking we would have done for the available languages, and then made them as, or used them to describe the hardware, right? If you look at the flow of any programming language, right? What is the flow, right? You use specifically a compiler to compile the source code, whatever you have written in a particular language, and then you translate the source code into, it checks the syntax, and the compiler converts into machine language instructions, right? The machine codes, and then that program is executed on a computer to obtain the desired output, a design result, right? That is what you will display in your standard output system, that is in monitor or any of the blocks, right? Other devices. So that is about software programming language. Now, hardware description language, what here the intention is to check, first come up with the modeling in order to model the hardware and build the structure. And what is our end goal? End goal is to build the ASIC or FPGA. So for instance, FPGA is also a semiconductor device, and goal is to build the device, build the hardware, right? So that is the main difference. So now the process here, it is the compilation, linking, and then getting the output, right? And then executing the program. Here, the flow of when you write the description, the hardware description language, the flow is what you have studied right from the architecture, and describing the architecture and the design using HDL, then taking it to synthesis, and further taking it to the physical design steps. Those are floor plan, placement, routing, and CTS, the clock tree synthesis, and further do the basic physical verification, and the logical output of the ASIC design or the FPGA design process is GDS2, that is graphic design system format, and that is the one which you give it to the foundry in order to manufacture the chip. This is what we use in the HDL. Okay. So now it's just a simple gate. I think most of you, this may be just as an example. You are aware of all these things, as Damodar is mentioning. Many of you are faculty members, right? So I'm just going through the flow. Okay, so just an AND gate, and so what is the structure we use in Verilog is the module and the module name, and what are the inputs we say, and then what is the output we say, and then now this is the behavior we are describing within the module and end module. So in Verilog, it's all about module, and all of your description is you're including in a module. And if you take Verilog, it has little different structure where it has entity which talks about different ports, what you are mentioning here, these ports, inputs and outputs, and in out also you can refer. And architecture is the way, a place where you describe the behavior. Okay, so this is the difference. Of course, I'll little bit touch upon the differences between Hdl and then Verilog going forward, because today it's about always Americas versus Europe, and Verilog is mainly America promoted language. So that way, Europe was initially they were using Vhdl. So that way, Europe and Canada still they use in defense industry still uses Vhdl language. And this, in fact, Vhdl is very good in order to closely look at and realize the hardware actually. So it's a tightly knit language to describe. C is, this Verilog is more like C language. Okay, so it is easy comparatively to write and then write the code and then visualize more like C language. But this pushes more towards the higher level language. This pushes more towards towards the hardware realization. Okay, so that is of course there is history to everything, right? And then HDL origin, it all started like this. In 1995, it was developed by a company called Gateway, and later it was acquired by Cadence Design Systems. Now it's part of this. And then what followed is they referred how Pascal and C languages were there, and then that's how. Also, Vhdl is a Department of Defense sponsored standard, and then it is similar to ADA, and of course both are IEEE standard today. So little bit here, what is the takeaway? In 1995, this 1364995. So this is Verilog 95. And later, today, if you look at, everyone is talking or using, even academia also, they know what's happening in the industry, that system Verilog, right? The system Verilog is a language, so which can be used both for design and verification. So it is the Verilog base is enhanced in order to 2001. So they call this as 1394 2001, and further in 2005, Verilog 2005, it was published. So now later, the enhancements done to Verilog were updated as System Verilog, and today System Verilog from 2005 further, we have 2017, 2018. Okay, so now the same Verilog is used as the base in order to come up with the system Verilog. Okay, in 2009, so this further upgraded, right? And then this is the SV, what we have the latest standard, or 1800 2017. So this is the history and also where we are today, the Verilog, and then further enhancements done and standardized as system Verilog. So the system Verilog, we call this as HDVL, where we use the system Verilog for hardware description and verification. Okay, so hardware design and verification language. So HDVL we call. Okay, of course there is for some time there were two tracks. Okay, where the design was done in Verilog or Vhdl, and verification, we were using languages like Specman E and Vera. Those kind of languages emerged in between actually for about 2 decades, and they were supporting more for verification. So this for verification, this for design, and somehow industry thought that it is too much of overhead of one more language, and also one more tool. Specman was used to compile this E language. The Testbench was written using Specman E, and then we were using separate tool. Okay, and similarly Vera as well. So that way, industry wanted to consolidate. That's where most of the features what this Specman and Vera were giving, like object-oriented concepts, randomization concepts, functional coverage concepts, all those they were brought into Verilog and then made as system Verilog. So we have one language for design and verification and one language for one tool to simulate. That is whatever cadence tool you use. It supports both Verilog, system Verilog, and even supporting methodology that is UVM. Okay, and earlier this Specman was brought a methodology called ERM, e-reuse methodology. All this were eating up a lot of time from the design and verification engineers, and also the computation time, because you are using one Hdl simulator, one Vera simulator, all that. So of course, these are all the things which happened, and in last 2-3 decades, and now everything is consolidated and converged and made it easy. And today everyone uses only system Verilog UVM is for verification, and system Verilog for design. Okay, of course, legacy design still Vhdl Verilog we carry, right, and we support. And it current simulators also give backward compatibility of previous HDLs what you have written. So just to compare Vhdl and then Verilog, so it is strongly typed language, and this is weakly typed in a sense that this how you can understand easily is each type, data type, once you declare, right, you can not assign to any other data type, right? So convert, and you have to use convert, conversions. Okay, but here at times you will declare a variable, and then you can assign to the other one. It may truncate, and then accordingly it will not give an error. But see, that's what the weakly typed language, the disadvantage is that, right, it may miss out the functionality what you wanted to intend, right? So that's where I was telling, the more restrictions are put, then later when you are realizing the hardware and the number of mistakes what number of issues what would come in the future, you could arrest at the time of coding itself. Okay, and Vhdl is not sensitive. Verilog is case sensitive. What it means, if I say integer variable when declaring, right, you can use either uppercase or the lowercase. Here it's all lowercase. So there are built-in types and logic presentation. This is extensible types and simulation engine. So it has, like I said, entity and architecture. Okay, it's all about module here, and you can describe all the models in both the languages. Complex data types in complex system. This is simple. See, all that what you will learn in Verilog, very important, reg and wire. Here, if you look at, there are multiple data types in VHDL. So packages are present as I showed you the first example, and as a library management, it is no package. I need not to include anything when I want to compile a Verilog code. So everything is built-in type, and directly I write a module. As long as I have a tool, I can compile. So it's all perception. Again, when you have directly started with Vhdl. Once you learned, that looks easier, right? Of course, I have worked on both Vhdl and Verilog. Of course, that's what is my experience in terms of this hardware related, right? This is very good actually, hardware related implementation. Okay. So now, like the same example, Vhdl code for this, right? This is the library and this library, and then this is including this package. Use this. So now std logic 116, just like your C program, hash include stdio.h. Stdio.h, what it has? It has your basic input output function, standard input output, where your printf, scanf were defined. Like that, std logic 1164 is having this std logic, right? So now std logic and stdu logic, there are different, some arithmetic functions you want to include, std logic arith, right? Unsigned. Like this, you have to include these packages in order to use any of these different constructs here. So of course, those are all defined when you learn Vhdl in case, and you will learn more about it. And then here, just giving the program structure of Verilog and Vhdl. Of course, like I mentioned, so here only about your module name. These are the ports, and then you are saying which are the inputs and outputs in this port list, and then this your combinatorial circuit design, directly assigning output Y is A, B, and that's it. Okay, so the end module. So this is the structure of Vhdl and Verilog and the basic difference. Now, I have taken one simple example in order to explain the Verilog program structure. So I think most of you have studied this, and multiplexer, simple multiplexer I have taken, and multiplexer, and the output is flopped. Output is given to a register, right? That is the one. In order to include both combinatorial and sequential parts here, I have taken this example. Okay, so what it has is 4 inputs and clock and reset inputs and select lines for the multiplexer. So this is the block diagram. Okay, and if you visualize this one, the multiplexer circuit inside the gate structure of the multiplexer is this part. Okay, and then registered output, I said the output part, I am taking it to the flip flop, and then with respect to the clock, I am just sampling and assigning to the Q, that is output. Okay, so what is the behavior of multiplexer? Right, you based on the select lines, the output mux out, either it passes I0 or I1, I2, I3. Okay, so it take multiple inputs, it can select any one of the input and then pass it to the output, right? So that is the behavior of multiplexer, and that's combining any of these and then sending it to the output. Okay, that is the truth table, right? Important is, without this understanding, Verilog is of no use. So especially when you are designing, you have to understand what is the circuit you want to build, and then it is easy for you to choose a particular construct in order to design. Okay, so now without the logic diagram or without the paperwork, we say what you want to design, directly coding, getting into the coding without proper design, right? So you will end up in doing a lot of rework. Okay, it will get into iteration, and finally, right, and you will spend a lot of time bring the desired hardware what you want to implement. Okay, so that is the multiplexer, and then the multiplexer output. Okay, so now if you want to write a Verilog program, right? So how do we do? So Verilog, like I said, the program structure, it has module and end module. Okay, so observe there is no semicolon here. There is semicolon here. So module name, you give your own user defined module name, and these are the ports. Ports means so basically, see, all this coming from my requirement. What is my requirement? This is the chip. This is the hardware. What I want to implement. This hardware will be having certain inputs and the outputs, right? And then finally, in order to model this, what is the first thing I would have? Okay, this whole thing, let me say, is a module, and this module name, you may want to give a name, right? And ports, these are the ports, inputs and outputs. Inputs and outputs, what a module should have, these are ports. Okay, then okay, ports are given. Now you will have to see which are the inputs and outputs. So that is, you can give the inputs, outputs you can define here. Okay, and of course parameters, we talk about it a little later. Of course, anything you want to customize, you want to design generic and then customize later. So in such cases, right, you use parameters. Okay, and I'm saying within the module what and all can come, right? And assign statements, these are concurrent, we call, and these are also used for designing combinatorial circuits. Initial statements, these are procedural. The moment you say concurrent, it is parallel. Okay, and when I say procedural, the it's in sequence, one after the other. Okay, and always statements, these are also procedural constructs in order to design the sequential circuits. Okay, so we learn all about this Verilog. That way it is easy to learn very few constructs, and for understanding, and you can learn easily. Okay. So now I have taken this Mux example, and this Mux example, all this whatever you saw, right, those I have listed in the port list. And now, which are the inputs? I have said, right, clock, reset, these are inputs. I0, I1, I2, you can as well, these you can write in the same line. It's okay. Give multiple, variables, input ports for one put. Output, you see, this is bus. Okay, bus means it is 2-bit. Select is 2-bit line. This is how I give this, define more than 1 bit. This is by default. This is 1 bit. These are all 1 bit or 1 line. Okay, output is 1 line. Okay, that's a module, and these are the ports, and these are IOs, right? And now this right now intermediate lines and the signals I'll be referring here. Okay, and these are wire and reg declarations. So when you want to declare a reg or wire, you can do like this. And further, now this is my multiplexer is a combinatorial circuit. Okay, so that way I have implemented using if else statement, is a ternary operator I have used in order to select any I0 to I3 selection logic is what you see in this. Okay, so basically how ternary works is, if select 1 is, let me see if there is a truth. Okay, so here if select or in the truth table, what you saw, when select 1 is it is 1, then what will be selected? This part. When this is select 1 is 0, it will be selected whole of this. Now inside this, okay, so select 1 is, this is select 1, this is select 0. When select 1 is 1, this will be selected. When then S0 is 0, then I3 will be selected. Now output will be I3. Now select 1 is 1, S0 is, when this is 0, I2 will be selected. Right? What did I say? Sorry. When select, when this is 1, right? When this is 1, I3. When this is 0, it goes to I2. Okay. And then this is about when S1 select 1 is 1. When select 1 is 0, it comes here. Now select it checks. Now select 1 is 0. When this is 0, select 0 is now 1. Selects I1. Okay, and then when select 1 is 0, select 0 is 0. Then what it selects? I0. So this is how it works. Okay, so just a ternary operator I just explained here. Okay, so now finally this is how the selection logic works here in this code. Okay, you can write if else statement. There are multiple ways to write this. I've chosen one way of implementing this. Okay, and now this is concurrent. Okay, and now this is always block. This is sequential circuit design where you are implementing. This is implemented with this line mux, and now this flip-flop implementation is using always passage of clock. Okay, so passage of the clock means when clock at the passage, what it has to do, every passage of the clock or reset. Or reset means whenever reset changes. Now, right at the reset also, it has to this is called sensitivity list, and it has to check. I'll explain in detail in the sequential circuits here just to understand. If not reset, Q out is 0. So this is active low reset. Whenever reset is 0, then output is 0. Then when reset is 1, then all the time, every clock, what it should do? It has to pass mux out to Q out. What is mux out? This one. So this mux out goes to the input to the flip-flop, and that's how it's connected. The moment you describe the hardware like this, that's how it is going to be behaving. Okay. Then finally, this Q out is assigned to this Q out because outputs actually should be of register type. Okay, so the Q out, if it is coming from a combinatorial sequential circuit, right? Because finally, this Q out has to be register type, right? And then this output Q, you are assigning this Q out to this Q. This is the port here. Okay, so of course, you can as well say output reg Q. Okay, you can directly assign to Q. That's also other way. So here, in order to explain what is this reg, right? I have anytime within always block, you want to assign all should be of reg type. Within always and within initial. Okay, within initial also it has to be reg type, and any of the things using assign, they should be of type wire. So this is a basic rule. Okay, so of course we will learn more, but this is the basic program structure, and I've taken in order to include in the example all types, both combinatorial and sequential circuits. I have taken here, and both reg and wire. So this is the basic Verilog program structure, and now this is the sensitivity list, right? And these are all the sequential statements where the execution happens one line after the other. So that is the program structure of Verilog. So we talk about three common abstracted models. So the last one, it's very switch level, which I'm not covering here, the transistor level modeling, right? And then you might study. That's where whenever I take sessions for academia, they ask, okay, so there is one more, which is transistor level, right? Yes, it is there. Of course, when we are talking about the Hdl part, in fact, the gate level, the structural model itself, we don't use much except for some primitives and other things. Okay. And so here I'm giving the structure. Of course, what is difference between reg and wire and positive triggered, all we will learn when it comes to sequential and combinatorial circuit. Just hold on till then. So we'll learn about the abstract, because without explaining the structure, if I put some examples, you will not be able to understand. That's why I'm taking an approach where whenever I put out a code, you understand the structure and the nitty-gritties of it, or the details about each of these syntax, right? We will deal with further, session. Data flow model is used for modeling concurrent statements, and it uses concurrent statements and using assign. Behavioral uses sequential constructs, rather procedural constructs. Structural gate level. So higher level models are constructed by interconnecting the lower level components using gates. Okay, these are the three structure. So see, it is all about theoretical understanding. Beyond a point, we don't too much differentiate. Is it behavioral? Is it data flow? We don't go too much into it. But in order to see and understand for learning purpose, I am putting out these differences. What is RTL? It is register transfer logic, right? It is register transfer level. So why we call this as register transfer? All that if you look at any circuit, right? Even the example what I gave, it's all about you have flip-flops, okay? The sequential element, storage elements, okay? And now in between there is combinatorial cloud, which is logic, right? Output of the flip-flop goes here, the combo logic, and this combo logic output is given here, and then this output of flip-flop, one another logic. So the whole chip, if you look at, this is the structure, okay? And RTL means now register transfer logic. Now these are all registers, okay? Now we transfer the values, right, from register to register. Of course, it goes through the intermediator, the combinatorial logic. So actually your design, your logic will be sitting in this combinatorial elements, and this sequential elements acts as transferring from one flop to the other, one register level to the other. So that's the basic understanding if you look at register transfer level. So it uses registers for storage, and then it transfers data between input, output, and the register using combinatorial logic. So where to the flip-flop data is coming from input, and then finally it goes to the output. Output and input, these are, they can realize that these are the pins of a particular IC. Okay. Of course, so the level of abstraction used in the HDL. So RTL, because finally you describe this behavior using language at abstract level. So that is what is abstraction level using Verilog. Now, example for data flow model. Okay. Like I said, current statement and using assign. Okay. And so you can for both for RTL and FPGA implementation, right? And the same multiplexer example if you take, right? So now this is an example for data flow model where I have used assign and concurrent statements and its combinatorial circuit. This is for data flow. Okay. Behavioral model, right? So it contains procedural statements, okay? And it uses always and or initial. Initial statements are executed only once. Always statements are executed repetitively. So this is based on the sensitivity list. For example, at passage of clock, what you have seen, every pass edge of the clock, it enters to this always block. But initial, and you're right, I'll show some examples where only once it executes and then it goes till the end. That's it. It will never come back to that line. Both combinatorial and sequential blocks can be designed easily using if else, case, for, and while. So basically, now in this behavioral model, within the always block or within the initial block, you will be using behavioral constructs like these. Actually, Verilog, it has very fewer number of things to know. Like I said, reg and var, integer, real data types, and initial and always procedural constructs assign for combinatorial circuit design. And within this procedural code, use either if else, case statement, for loop, or while loop. This forms very much, I would say 50 to 60% of your Verilog will be around these constructs. Okay. Rest of it, some of these are more for verification, like parameters we use and tick defines and tick time scale and dollar display, dollar monitor, those for debug, right? Read my match, write my match. So most of it, if you look at additionally what you learn, those are verification. So all are, of course, now I'm saying verification design. What is the difference, sir? Okay, so then I'll come to that synthesizable and non-synthesizable construct little later. Okay, so but pretty much, that is it actually. So now the initial, it is used only in the test benches verification. This is not synthesizable. Okay, non-synthesizable. Always it's synthesizable. Behavioral model is more efficient for speed of execution. Okay, and now the same Mux code you can using always at. Now always it is not reserved for only positive, right? No rights, no exclusive rights for that. You can use any, you can include any signal, right? At means any change happening in any of these signals, you come here and then you execute, okay, case statement, right? So the when it is 0, I naught assigned to Q, when it is 0, 1, I1 to Q, right? So that's how you can relate to. Okay, of course, there's a default, the case statements when you come, right? So case, end case, default. So in Verilog, syntactically, what to be noted is this semicolons where to use, right? Where you should not use semicolons. Okay, first thing. Second thing is where you have to use begin and end. Okay, so typically, whenever there is a more than one statement within a procedural construct, you go for begin and end. Okay, whether it is within always, whether it is even here case, end case, right? So you are, it's starting, you can as well put begin and end before the case here. Let us say within this case statement, you want to put more than one statement here, then you put begin and end here. Similarly, if else statement like this. These are some of the things which you can remember for your easy execution of the code. Otherwise, you will spend a lot of time in debugging the codes. That is about the modeling. Okay? So gate level are structural model, okay, which are at a lower level. What is lower level here? The gate level. That is the level of abstraction you can go, right? Using Verilog. Further, if you want to go, that is what I was referring to, the transistor or switch level modeling. Okay. So gate level modeling is also called structural model. Okay. And however, now if you design like this, the entry of code is time consuming. With the example, you can understand better. So there are some effective ways of modeling the gate structure, that is gate primitives, which are built in, or some of them are can be written. So the gate level structuring used for building these gate primitives. Those are optimum representation of a particular behavior of a gate. Let us say AND gate, 2 input AND gate, primitives. So inputs and the outputs are for all possible inputs. What are the outputs will be clearly modeled using gate primitives. Okay. So gate primitives are predefined in Verilog, which are ready to use. So they are instantiated like tools. Okay. So multiple input gate primitives. single input. Okay, so these are not so important for you, but know it. There are some gate primitives for all these gates. These are for basic gates. There are gate primitives, like I said, multiple input gate and single input. For example, now, what is that? NOT gate could be one single input, and then this multiple input AND gate, 2 input AND gate, 3 input AND gate, like that we can. Gate level structure is appropriate or components are available and need to interconnect. And like I was telling, single input primitives include these buffers and NOT gates, right? Let us say, see this is built-in primitive NOT gate, you're instantiating, and then input and output, inverting a gate, buffer, all right? So input, and you can have 2 output buffer, okay? So something like this, one input, and then so in order to drive, let us say 2 next gates, right? It is giving 2 inputs, right? And this one tri-state buffer, okay? Tri-state buffer. So basically tri-state buffer is represented using input, output, control, enable. So like this, you can implement this. And wire 3:0 out in 0 in 1 signal declarations. This is 4-bit, and then array. This is actually, so how many AND gates here? AND gate 3 down to 0. So 4 AND gate instantiation of 2 4-bit input vectors. So you will understand more. So here the gate level structures and gate level primitives. These are all the primitives, like I said. This is buffer if 1, buffer if 0, not if 1, buffer if 0, not if 0, right? So these are the enable, buffer, and the NOT gate, okay? And so for the multiplexer, the same example I am representing using gate level like this. Now I use these available gates. Now I described the same set of inputs, right? And now look at this. How many gates here? 2 NOT gates. I've instantiated 2 NOT gates. And how many AND gates? 4 AND gates, and then 1 OR gate. Now I am connecting, let us say S1 bar, S0 bar. Where is S0 bar, S1 bar? Here. This is S0 bar. This is S1 bar, right? Not and S1. Now come to U3, right? U3, let us say this T1, this is output, right? I0, let us say I0 is one input. S0 bar is the other input. See this S0 bar, other input which is coming here. And S1 bar is the other one. Okay, so now output is T1. So like this 4 are modeled. And finally, all the outputs T1, T2, T3, T4 are the inputs to OR gate, and this is Q. This is the output. This is the output, and these 4 are inputs. So look at, this is where I was telling gate level is time consuming. Now, each gate you are describing using the basic primitives or the gate primitives or the gate models available. Okay. Now, okay, sir, all this is fine. Now, which one to use? You are confusing us, right? So actually, we use as designers mix of all the 3, right? So maybe looking at we may use more of behavioral. Of course, for designing combinatorial circuits, as you saw, assign kind of statements, we use data flow model as well. So overall, we use the mix of all the 3 in order to design. But at the end of the day, in your test bench specifically, you use more of behavioral, okay, behavioral, because your structure is not important for your test bench. It's all you have to generate stimulus and then apply. Then you don't too much worry about whether it gets converted into gates. That's what is synthesis process. Synthesis is a process of converting RTL to gates. Now, I am not synthesizing my test bench code. Okay, hope you are understanding. What I meant is, this is your design, this is your test bench. In order to apply stimulus and get the outputs and then check. This is my test bench code. Now this, what I am saying, I use more of behavioral. This here, I use mix of all the three. Okay, and this is synthesizable. This need not be synthesizable. Okay, non-synthesizable. So finally, what is synthesis? Like I said, this should be converted to, should be mappable to gates. This one need not be. Okay, so that is where I don't worry about the either use assign statement, always statement, or whatever, right? Initial statement. I don't care here, but I do care here. I can use only assign and always. I cannot use initial here. I cannot use timing delays here, right? Lot of constraints, because finally it has to be translated into gates, right? Otherwise, this that's where the HDL part comes into picture. Yeah. So I think we can execute the very first program. I think demo we can go through. Avinash, are you there? Can we do the explain the tool related and execute this first program for them? Avinash, Damodar, anyone there from Multiple?
Hello, sir. I think Saraswati have joined the session, sir.
Yes, sir.
Yeah.
Yes, sir.
Yeah, so now you can walk them through the tool flow, right? So that
Yes.
when we get into the codes and when we demonstrate examples, they'll be able to easily follow.
Okay, sir. Fine, sir.
Huh? Okay,
Yeah.
so Surendra sir, do you want to give a break or should we continue with the tool demo?
After that demo, what will you do?
After
We'll
the demo,
continue.
we'll get into the Verilog constructs learning.
Okay. Okay. So I think we will have a 10-15 minutes break. At least 10 to 15 minutes.
Yeah.
Huh?
So now
Okay.
11:15, we will resume at 11:30.
Yeah. So this meeting will be on as it is. So
Yeah.
I request participants to kind of an emergency break, you can say, urgent break. So let us have a 10 to 15 minutes break and then come back. 11:30 we are going to sharp start. Okay.
Yes,
So,
11:30 sharp we will start. But then we'll
okay.
start the program demo and then we'll walk through the constructs and then we'll continue.
Okay.
Okay.
Anybody has any questions? Anybody has any questions up till now?
Yeah.
Sir,
So,
chat box, you can see few questions were there. I suppose one or two.
so now reg and wire, I will explain. Basically, reg is for sequential circuit, wire is for combinatorial circuits. I'll explain more about it. And is positive edge triggered? Yes, that's what positive is the use for positive edge. So sensitivity, whenever clock logic is rising from 0 to 1, that is pos edge, right? You sample, right? Or you enter into the always block. That's what it means.
Yes. Okay. Thank you. So we'll meet after 15 minutes.
Yeah. Yes. So like legacy Verilog still today, even today, designers who knows Verilog is good enough. Okay. But they are not leaving Verilog. Okay. It's not about leaving Verilog, because one reason is they know Verilog. Second reason is that System Verilog doesn't provide too many constructs for design. It has added only fewer number of enhanced constructs for designing. It's more about verification. System Verilog adds more for verification than design. So that way, Verilog is still industry The whole industry follows Verilog for. They may name the file as SV code today, right, for compilation other reasons, but otherwise .v or .sv, not too many is constructs from system Verilog for design. Okay, that's the reason. Harish, ಈಗ it is what is full lab ಅಂತನಾ? ಸೊ ಈಗ ನಾವು ಇಟ್ಸ್ ಓಕೆ ಆಕ್ಚುಲಿ ಈಗ ಫಸ್ಟ್ ಹಾಫ್ ಅಲ್ಲಿ 11:30 to around 12:30 I will walk through certain constructs rest of the class. So ಈಗ ಅದರಲ್ಲಿ ನಾವು to pick up the programs let us say ಆಮೇಲೆ 1 to 2, 2 to 5, 3 hours, 2 to 4 hours. Okay, look at the time. ಅಷ್ಟರಲ್ಲಿ can you engage them 2 hours ಅವ್ರಿಗೆ ಬರೀ ಲ್ಯಾಬ್ ಮಾಡ್ತೀನಿ. ಇಲ್ಲ ಅಂದ್ರೆ ಒಂದ್ ಕೆಲಸ ಮಾಡೋಣ, ಈಗ ಡೆಮೋನು ಸರಸ್ವತಿ ಮಾಡೋದು ಬೇಡ, ಆಫ್ಟರ್ನೂನ್ ಅಲ್ಲಿ ಡೆಮೋ ಇಂದಾನೆ ಶುರು ಮಾಡ್ಬೇಡ, ಲಿಟ್ಲ್ ಬಿಟ್ ಚೇಂಜ್ ಮಾಡ್ಕೊಳ್ಳೋಣ ಅಲ್ವಾ? ಹಾ, ಸೊ ಅಲ್ಲಿಂದ ಶುರು ಮಾಡ್ಬಿಟ್ಟು ಆಮೇಲೆ ಡೇಟಾ ಟೈಪ್ ಇಂದ ಹಿಡಿದು ಓಕೆ ಈ ಫಸ್ಟ್ ಪ್ರೋಗ್ರಾಮ್ ಇಂದ ಹಿಡಿದು ರೈಟ್ ಫಸ್ಟ್ ಪ್ರೋಗ್ರಾಮ್ ಸ್ಟಾರ್ಟ್ ವಿತ್ ದಟ್ ಅದಾದ್ಮೇಲೆ ದೆನ್ ಡೇಟಾ ಟೈಪ್ಸ್ ಮತ್ತೆ ಪೋಸ್ಟ್ ಕೇಸ್ ಸ್ಟೇಟ್ಮೆಂಟ್ಗಳು ನಾವೇನೇನ್ ಮಾಡಿರ್ತೀವಿ just note down what are the topics we dealt today. Other examples are one by one, line by line, you can just walk them through. And then slowly you can just spend time and answering the questions and you can engage alva. Okay. I can big up put one on Sparto and at the same time that's what they call it. I will just tell them. Yes, sir.
Shivappa, sir, I'll have to change the control, no? I'll have to put the control.
ಒಂದು ದಿನ ಹರೀಶ್ ಹತ್ರ ಮಾತಾಡ್ತಿದ್ದೆ, ಈಗ ಡೆಮೋನು ಮಧ್ಯಾಹ್ನನೇ ಮಾಡ್ಬೇಡ, 2 o'clock ಇಂದ you and Harish engage them. First you do the demo of the tool ಮತ್ತೆ ಅದರಲ್ಲಿ ಏನೇನು ನಮ್ಮದು ಹೇಳಿದ್ರೆ ಅದೆಲ್ಲ ಮಾಡಿ. ಓಕೆ, ಅದ್ ಮಾಡಿದ್ಮೇಲೆ ಹರೀಶ್ ವಿಲ್ ಸಪೋರ್ಟ್ ಆನ್ ಪ್ರೋಗ್ರಾಮ್ಸ್ ಏನ್ ನಾನು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತೀನಿ ಕನ್ಸೋಲ್ಸ್ ಗಳು ಅದೆಲ್ಲ ನಾನು 1 by 1 ನೀವು ಎಕ್ಸಿಕ್ಯೂಟ್ ಅಂಡ್ ದೆನ್ do the demonstration in the after you are done. Do you have any programs? ಈಗ ನಿಮ್ದು ಏನಾದ್ರು programs ಎಕ್ಸ್ಪೆಕ್ಟ್ ಮಾಡೋದಿದೆಯಾ? ಅಷ್ಟೇ ಅಲ್ವಾ? ಓಕೆ, ಟೂಲ್ ಕನೆಕ್ಟೆಡ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಾದ್ಮೇಲೆ ದೆನ್ ಫಸ್ಟ್ ಪ್ರೋಗ್ರಾಮ್ ಇಂದ ಹಿಡಿದು ದೆನ್ ಹರೀಶ್ ವಿಲ್ ಟೇಕ್ ಓವರ್. ಸೊ ಈಗ ನಾನು ಏನ್ ಮಾಡ್ತೀನಿ, ಐ ಸೆಡ್ ಟೂಲ್ ಡೆಮೋ, ಐ ವಿಲ್ ಸ್ಕಿಪ್ ಇಟ್ ನಾವು, ಈಗೇನು ಮಾಡೋದು ಬೇಡ, 2 o'clock ಇಂದಾನೆ ಶುರು ಮಾಡ್ಬೇಡ ಅಲ್ಲಿ. ನಾನೀಗ ಕಂಟಿನ್ಯೂ ವಿತ್ ದ ಥಿಯರಿ, ಕಂಪೈಲೇಷನ್ ಪ್ರಾಸೆಸ್ ಇದೆಲ್ಲ ಮಾಡ್ತಾರಪ್ಪ ಇದೇನಂತ ನಾನು ಹೇಳ್ಬಿಟ್ಟು ಇದು ಕಂಟಿನ್ಯೂ. ಓಕೆ, ಎನಿಥಿಂಗ್ ಎಲ್ಸ್ ಇಂಪಾರ್ಟೆಂಟ್? Okay.
Shivappa, sir. Hello, Shivappa. Shivappa sir. Hello. Okay. Yeah. Shivappa. Yes. Pal madam. Pal madam.
यस सर
हाँ मैं बोल आप यू आर देयर ठीक है मैं बोला मेरा आवाज जा रहा है ओके
नहीं आ रहा है
ओके नॉट रिस्पॉन्ड
I will continue. So one small change. So we will do the demo and also all the lab in the afternoon. So I will continue with my session further. Okay. So let us take the same example, right? So for our understanding, the multiplexer with the registered output, right? And now this is the design. This is the design. And now, how do we verify? The word what we use more often is verification in the ASIC world, rather testing. Okay, testing specifically we use for board, testing, right? Or the test that is DFT, design for testability. There are different contexts where we use the word test. Actually, the here more of we use one is test bench. Is one word. Other is verification. Okay, and now this is the design with these inputs and outputs. And now we want to verify, right? And now in order to verify, I will have to write the test bench, or I will have to build the test bench. What test bench does is it generates and then applies input to the drives the values to the inputs, and it collects the data whatever is coming at the output pins, right? Outputs of the design, right? So that is the test bench concept. Okay. So now you will see some of these new constructs. So tick time scale. Briefly, I will tell about this. In the simulation world, you will have to mention the time units and the time precision. Now this one ns is the time unit, and the other one, this is precision. Okay, so that we use tick time scale. And now anytime if you want to include other files where you are instantiating or using in the current, just like your include in another language, use tick include, and this particular file which is there in program directory, and then this design file. Okay, and now this is my test bench module. So typically now if you look at this test bench, it doesn't have any ports, no inputs and outputs at the top level. Now you have this design, right, which is this Mux FFEX, this, and this is the one which you will be instantiating here and then connecting and driving. So what is the scheme we are going to use? We use this design and we drive the inputs, and then we collect the outputs in this infrastructure. Test bench is about infrastructure for verification, just like your lab setup. Like that, you are building a bench for testing, right? Now, inside module, 1 minute, just give me a moment. Sorry about some disruption. Okay. So now what I was telling, I was explaining about the test bench structure, where you are creating the test bench in order to verify this block. And now all these ports you want to either drive or collect data, right, from the outputs. So now those you are declaring here as registers, like for example, reset 10 underscore TB. Now I am declaring this signals in order to connect and drive these respective ports. Okay, and output, whatever I am driving or reg, whatever I am collecting, the output are wire here. Okay, now this is the other part where DUT instantiation, where this design is instantiated inside this test bench. Now this is the design module name, and this is the instance name. And now positionally, now it was having all these inputs and outputs. Now you are writing here I0 TB, say I0 TB, is connecting here. So I1 TB is here. So that way, this is how you are declaring these local variable. These are local to this test bench, and then you are connecting to the module in the instantiation, right? This is how we instantiate the design one module in the other module, whether it is test bench or design. Here it happens to be this is design, you are instantiating inside the test bench. Let us say this is top level module. When you are constructing a hierarchical design, there could be multiple blocks which you are instantiating. That we will see some examples, going forward. So right now I am instantiating the design in the test bench. Now let us look at, okay, now structurally I connected, instantiated the design, and I declared the variables required, either reg or wire. Now I declared one integer also here. Okay, so watch out what you observe new things, what you see in the program structure here. It is integer, one more data type. Okay, so it's a 32-bit integer value. Now clock generation. Now there is a clock, right? Now always #5 clock TB, not of clock TB. This is how I write. What it means is now clock TB is a register and it inverts, right? It complements after every 5 time units. Now this 5 time units is mapping to this unit. Okay, #5 means 5 nano, right? And now every 5 nanosecond so this is 5 high time and then another 5 low time. So like this it complements, right? It inverts the outputs. So finally always means always you will get it is generating, it's a free running clock. Free running clock is what you are generating here. So this is your test bench. Okay, now what is next? You have generated the clock. Now is reset. Initially you will reset, right? So now what is new here? Initial. Like I said, always it enters, but initial only once it executes. Now it prints, Verilog Testbench running, right? So just like your printf statement, we use $display. Okay, $time means at what time this is printing, right? It prints this. So you'll see more of these constructs in this, today and tomorrow. Okay, and you will become familiar. First time when you see, right, it may be too much or unfamiliar things, right? So don't worry. So we will use these repetitively. Okay. And now reset and TB is equal to 0, clock TB is equal to 0. Now we initialize clock and reset, right, with 0. Now if it is inverting here, what is the initial value? Clock TB should have some initial value that it will complement. That's what I am saying. Initial value is 0. That you complement, it will become 1, right? Like that. So reset is 0. Now what is next? Some values to these inputs. I0 TB, I1 TB, I2 TB, I3 TB. I am assigning to be in the safer side. I want to give different values 0, 1, X, and Z. Now these are the states. X is unknown, Z is high impedance state, logic 0, logic 1. These are the four states what we use in hardware representation. Any of these reg and wire can take any of these four states. Okay, so we will see more. Now select, initially I made it 0. Now initial reset is 0. After 6 time units means 6 nanosecond. See, most of the time you are talking about whenever #5 is or #10, some delays you see is, in order to give delay is what we use this one. You will say 6 means 6 nanosecond. No, here the time unit is 1 nanosecond, then you can say 6 nanosecond. If this is picosecond, this is 6 picosecond. If this is some microsecond, This is 6 months. Okay, so that's how you have to understand this. Now, after 6 time units, 6 nanosecond here, it comes out of the set. Okay, this reset is equal to 1 after 6 nanosecond. Then I declared one integer. For this integer count 4 times, I am doing something like this. Wait for 10 time units, and I am, what is count? 0. Now you see here, what is select TB? Select TB I have declared as register. What is count? Count is integer. Now I am assigning integer variable to reg variable. Here it allows. This is where I say it is Verilog is weakly typed language. Vhdl, you cannot assign any std logic to integer, integer to std logic. Here it is possible. That's where the difference between strongly typed language and then weakly typed language. One of the examples. Right? Okay. Now, if count is 0 and qtb, what should be the output when count is 0? Count is 0 means what? Select tb is 0. When select tb is 0, qtb should be I naught. That's what I am checking here. If it is not, right? If it is not, I want to print error. Or count is 1, qtb not I1, count is 2, count is 3. So for all these, checking those respective outputs, if they are not, I am printing an error. Here I am printing an error, $display error data mismatch. Count is this. Actually, this is format printing. Okay, so a count and then Q2B will be printed. Okay, and else pass data matched. This is my checking part. This is my stimulus part. Reset I applied, and I'm checking this, and then finally I end my simulation. Now, if you look at initial executes like this, right, it will not go back here. That's what it executes once, and then okay, that is about the first program and the design and Testbench. See, many times you might have used waveform viewer directly to inject the stimulus. You might have done that, right? So that's not industry way of doing things, because lot of variations, lot of you the design by giving all possible inputs in different sequences, and you have to stress the design. So that is where you have to write the test bench in order to verify. So verify, and okay. So now I have just random, and then you can stress the design, and so that here in order I am generating count 0 1 2 3, that is select tb 0 1 2 3. What if after I3, after I2 comes what? All those kind of variations you can check, and applying reset in the middle, right? There are many things what you can check. That's what real verification is. Okay, so except that specific formatting like $display this $time and those kind of doubts in the flow design and writing test bench, the flow is that understood. Any doubts at this level except the syntax. Specific to syntax is what is our next upcoming session is about, but the overall structure and then the approach, did you understand? Any doubts there? So finally you get the output. Okay, so this is time, because I have said $time here is a system task. Zero's time Verilog Testbench running. This is printed. And next is now 16, 26, 36. These are the time where data matched, right? Now this checking part. Okay. So actually, after in the zero simulation, in reset also will come, and then reset after 6 nanosecond. After that, you get these messages. Okay. So now that is now the steps to simulated design. Okay. Verilog design. What is the prerequisite? You should have EDA2 license settings available, and most of the time the industry uses all the time Linux environment, and here we use Cadence Incisive Enterprise Simulator IES. Okay, so see, you may have Model Sim student version and other EDA playground, all that you may have, but Linux environment we are using this. Other simulators available: VCS from Synopsys, QuestaSim from Mentor Graphics, right? And of course, there are FPGA simulators like Xilinx ISE, Xilinx Vivado. These are also you can use. Now, there are 3 steps in order to design. One is compilation, other is elaboration, third is simulation. Now, what is compilation? It's a process to check the correct Verilog syntax and the usage. That's compilation. Inputs supplied or Verilog design and Testbench codes for compilation. Outputs, compiled database created and mapped library, if successful, generates report, else error. Okay, in the reported, error is reported in the log file. Steps for compilation. Create work or library directory. See, in the latest tools, if you use, I think Cadence older version, you will use some cds.lib, right? Hdl.var, all that you do, the library mapping and Hdl.var. So these are in the older version. So that's where you create this library and then map all that you do using this. But most of these latest simulation tools, they will do that automatically. And mapping the work to library created, right? And then run the compile command with compile options. For example, now Cadence IES command only for compilation. Today we use NC Verilog plus access RWC. Basically, this is command for compilation, NC Verilog command. These are options. For example, plus access plus RWC means what? This is whatever created library you are giving access, read, write, and connectivity. Okay, so connectivity comes in the when you are simulating the capturing, right? That is the connectivity part actually. Now minus compile, because NC Verilog same you use, and when you don't use this minus compile, it does everything. Everything means what? Compilation, elaboration, simulation. Now I want that to do only compilation. Okay, check the syntax. You can give the Verilog file here. That's about compilation. Now elaboration. See, any simulator, any tool, you might have, even when you are compiling program, what you do, GCC, RCC, C++ or CPP, whatever you use, and then you give the file name, .c file name. But in between, by default, when you do what happens? Out will, let us say the executable name what you want to create is some program.out. Then what you see? -o, then program.out. Right? Like that, whatever -o, that is a compiler option. Like this here, whatever plus access RWC I told here is the simulator option. So now all the commands, whenever you are using, you have n number of such options you can use, appropriately. elaboration. What is elaboration? It is to check the port connections in hierarchical design. Now you have instantiated the design in the test bench and you have connected the ports of the design from the signals which you have defined or declared in the test bench. Is the connection proper? That kind of things are checked in the elaboration. Okay. So hierarchically, the database is built and then mapped to library. And if it is not correct, it generates error. Now, same NC Verilog minus elaborate will do the elaboration. Minus elaborate. Finally, simulation. Okay. Now simulate with given test vectors over a period of time to observe the output behavior. Inputs compile elaborated top level module name and output. Test simulation, run the simulation command. NC Verilog. This is if you want GUI mode. GUI means graphic user interface. It will bring up the NCSIM window. Minus R, and whatever you've created, it's available in this lib. Work lib mux ffextb. So told automatically it will create the default library, right? And default NC Verilog is creating work clip library, and in that library it has compiled and put that database is the name of the top level module, that is mux ffextb, that is top level. Further is instantiated, it is having the instantiation of mux ffex inside the tb, right? And you're pointing to this lib in order to simulate. Okay, so now these three steps are the basic for simulation. First is compilation to check the syntax, elaboration whether hierarchically things are built properly will be checked. Third is the simulation, simulate over a period of time by applying the stimulus is checked in the simulation process. Same thing if you want to run in command mode, means in the terminal itself, that's what you will see in the afternoon. Okay, and it bring up GUI and it will be compiled in the command line itself. Sorry, simulated in the command line itself, and the output what I showed you. So now last part in design verification, very important aspect is the debug. Debug means, right? So you have design, you have written test bench. Now, how do you know? I want to make sure first my test bench is correct before I verify the design. Now, am I doing right things in my test bench? Right? And that is first thing, right? You will have to use some display statements and all in order to check your own stimulus. And the second thing is now then whether the outputs of the design are correct. Now we use the messages in the log file and the waveform viewer for debugging the design, debugging our test. Make sure that, for example, now in that reset, it is up to 6 nanosecond, your reset is 0. After that, it is high. And next is clock. If you look at, see here, every 5 nanosecond, it is changing. Free running clock. Select 1, 0. You know what are the values you have given. For example, I gave 0 for some time. Then 1 I gave. That count value, which I assigned to select. Here, the values what you are seeing is select, I0, I1, I2. Where are they coming from? Select TB, I0 TB, I1 TB is where I am assigning, but those are the ones which are connected to these ports, and you are checking these values. So now these are the selects, and I0 I made 0. Throughout in my test bench I made I1 1, I2 is X. Usually simulator, someone was asking X, Z and all. Now you can see how X is represented in the simulation. Now it is X is unknown. Unknown means what? there is nothing in the hardware world. It is either 0 or 1 is what we say, right? Either it could be 0 or 1, but we don't know. That is represented in the simulator with X. Z is high impedance state. I think most of you have studied the electronics and the electrical characteristics, basic signal, right? So logic 1, logic 0. So there is intermediary, right? This is high impedance state where this one with little effort can be pulled to high or low. That is what is represented as high impedance state at a logic level. Of course, electrical level, you know better than me. At logical level, you can, this is also called impedance state or tri-state. Tri-state. So that representation is done with Z, and in impedance, the color combination what they use for representing Z. Okay, now these are the signal representations in the inputs, and mux out is the output. Okay, now whenever select is 0, what should be the output? Mux out 0. This 0 is passed to mux out, and whenever 1, 1, whenever 2, I2, that is X, X is passed here, and whenever 3, I3, it is the mux out. Then mux out is given to a flip-flop. Now flip-flop behavior is what? Every passage of the clock, look at this, what this guy is doing. Every passage of the clock, he is sampling mux out and giving it at the Q. So 0 was sampled here, 0 he gave. And then here, he still sampled 0 and he gave 0 here. He is sampling only at these edges. Now here, he sampled mux out as 1 and came here. And in this, he sampled this output as X. X came here, mux out, okay, from mux out. And then here, what is sampled? Z. Okay, sorry. So this one is passed to this Q. Now look at Q and Q out, what I have defined as reg, right? That's the output. Now this is a simple simulation first program, what you will see as part of our demo in the afternoon, right? So this is how we design, we simulate, we write test bench, and we compile, we elaborate, and we debug. Look at, now I look at the behavior, okay, what is that I'm expecting, and then one way of checking is I'm already doing comparing in my program whether Q is correct. That is one. Now you can also look at the waveform, double check whether it properly as per the design. Okay, so that is what is the initial introduction and the first program and process I have. So any questions? Is all everything going fine?
Anybody has any doubts? You want to, or any, you can ask anything. So please discuss freely.
Monotonous also. Okay. So we'll continue. Now, to the constructs, understanding various Verilog constructs available, and few of them I've already introduced, and specifics of it, and like I was saying, fewer number of constructs in Verilog, very powerful, and the concepts also, blocking functions, tasks. So these concepts we will understand how we write and then how we use. So how I have structured is, now the introduction part is over, HDL modeling. Now Verilog constructs, briefly I walk through most of the constructs, okay, and then combinatorial circuits and sequential circuit design, because directly when I get into the combinatorial or sequential circuits, some of these constructs will be left out because I may not use all these, all the Verilog constructs. So then I thought, let me introduce all which is available and then get into the specific design of combinatorial and sequential circuits. That way, you can apply your familiarity of these Verilog construct learning to design combinatorial and sequential circuits. Now, this is these are the keywords which were available in Verilog 95 and enhancements done with Verilog 2001. So I have not put that 2005 to 2018. That is what it is, system Verilog. So as long as you talk about Verilog, right? So these are the ones which we use. Okay. So for example, enhancements here, generate and local param and value plus args, and if not def, if not defined, else if some of these are added, power operator, right, 2 to the power of this thing, right? So all these are added on top of Verilog 95, and then that was published as Verilog 2001 IEEE standard. Okay, so otherwise the basic constraints, look at this: module, parameter, functions and tasks, always at, assign, dollar finish. So these are file operations we generally don't use. Dollar display, dollar write for debug, for printing the messages, dollar monitor. And these are pre-compiler statements: tick define, tick if def, else, include, tick timescale, and initial. Now disable, like some loops it is used, and events, and wait at port join, wire reg, okay, integer real, time, and factor arrays and 2D memory. So these are the things. Of course, begin and end, while, forever, equals, repeat, and some operators are there. So we will just go through. So this is summary of constructs of system. Sorry, very good. So I have tried to differentiate which are the constructs which are synthesizable and which are the non-synthesizable, because I know in industry there is a clear demarcation between designer and verification engineer. Verification engineer need not have to know really all the constructs which are synthesizable. Of course, out of interest and all that is fine, but earlier days, one person was designing, verifying, and doing the physical design. Even the board design, same engineer was doing. That was some 20 years back, 25 years back. Later, everything became a separate branch, separate, science actually. Now, architect is different, designer is different, and verification engineer, and further synthesis engineer. Synthesis, who can do synthesis and static timing analysis. Further, physical design engineer, okay, who does the floor plan, placement, and routing. DFT engineer, design for testability. Now, even now, PD engineer doesn't do physical verification. There is separate, team for doing physical verification aspects. So that way, it's all branched out, but that is the industry part. Now, when you are, maybe when you're doing a project, right, or guiding a project, you may ask your students to do the design, verify, prove the result. Probably you may ask them to put into FPGA and then demonstrate, because I heard, industry, sorry, academia will not recognize only simulation. They want to see something on the hardware working, right? That can happen. So those are good things actually, because you will know for one simple example, end to end, how to do things. That is. So in that aspect, this slide is very useful for you. Okay. Module, all I mentioned in this blue color are keywords which are synthesizable. Okay, which are synthesizable, can be used for design. All in red color, not synthesizable. Okay. And of course, the pre-compiler in both, right? And these are the set of constructs further, which we think, if you notice, see this initial, repeat, forever, wait, tasks, which use time, okay? Fork and join, we will learn parallel processing, right? Parallel threads, event. These are all display or this debug related. This is read mem, write mem, file operations to read the memory and write from the memory. Test plus arg, value plus arg. If you look at all these, whichever marked in red, those things, if you use in the design, they are not synthesizable. They are synthesis tool cannot produce a specific hardware for such constructs. Okay, so for rest all, most of it, it will be able to generate the equivalent hardware. That's where we segregate which are synthesizable constructs and which are non-synthesizable constructs. So in Verilog, we use commenting, single line commenting with /, two /, and C line commenting you can use for this block comment. So we have these operators. Okay, so all these as is given in Verilog. Of late, I came across. I had not referred much of the books academia is using today, but out of curiosity, I just spent some time, and these are the books which are very good actually. This digital system design title maybe a little bit different name. I'm just giving the references. Digital System Design Using Verilog by Charles Roth. This is a very good book actually. Charles Roth, which we're referring already. And one more to name is this one, Ashington, right? Digital Design and Embedded Systems Approach Using Verilog. These two are good references which I can mention here. And then even Digital System Design Practice by Ming Bolin. These you might be already using it, but they are the good ones which I found. They have explained even combinatorial circuit, sequential circuit design with example codes, and even exercises also, whatever they are given, I found they are very useful. So people who are interested in getting into VLSI career, and if you execute those programs, that will be very good, and then so it helps actually. So why I'm mentioning this is all these operators and the basic language constructs, right? So you can refer from there as well. Now just you can go through the bitwise. Bitwise means bit by bit the operation, whether AND operation or invert operation. operation, right? This is exclusive OR and exclusive NOR. This is left shift, right shift, and this is result, right? Let us say you have ampersand m1011 is the value. When you say ampersand m is equal to 1011, what it means is 1 and with 1 and with 0, and the result is and with 1, result is and with 1, final result is 1 bit. That's what is this unary reduction operator. Okay, so NAND all bits in m together, right? And like this, or NOR. So this is the unary operator. So logical operators, right? This we use not, right? Not of m, just not of reset, which I was using. If reset, if m is equal to 0, is equivalent to if m is equal to 0, right? If both m and n are true, right? And then this is r, either m or. This is basic. Now equality and relational operators. So we use double equals in order to compare, right? Not of equals, right? And this one less than, greater than, less than, or equal to. Now identity operators, this one, right, it's only two states, that is 0 and 1 in any variable. Only two states comparison is done by double equals. Now triple equals compares even if it is x or z. That's how, that's the difference between this and triple equals. See, don't get confused. Any value, Verilog variable can 4 states, 0, 1, x, z, which I explained. Now, when you want to compare these x and z, right, you use triple equals. So someone is asking, available in Google. Take it. You can download. Okay, so just I'm talking about the highlights here. Other operators, this is conditional operator, which I explained. This question mark equals, right? Select, this is the usage. If it is 1, m. If it is 0, go to n. This is concatenation. So you want to concatenate 2 bits, 3 bits, whatever, m and n, put it in this braces. Now replicate inner concatenation n times. N times this concatenation is replicated. Okay, so this is trigger an event. So event triggering, we use this part. So you declare an event, trigger this event, and then you wait for the event. We do with at. Okay, so now arithmetic operators. Okay, and this triple equals, triple less than, greater than, shift. Those are logical shift. These are arithmetic shift. Arithmetic shift, right? You know what happens, right? Shift m n times, filling with 0, and then here n times fill the sign bit. That's what happens here. M to the power of n, use, right? This is modulus, the remainder, m by n. Now with all these operators, you know, any language gives the operator precedence, because if all given in one line, right, which one to evaluate first, it goes like this. Okay, these IS precedence and then till this. That is the precedence order, what Verilog prescribes. So now I've already given enough introduction about this program and also what a simple Verilog structure will be, right? And it contains the parameters, inputs, output, and ports, assignment, concurrent, procedural, right? All this. Okay. So now, if you take a full adder example, simple full adder module A, B, and carry in, sum out, sum and then carry out. Give all the ports A, B, C in, S, C out, input A, B, C in, output S and C out, right? Now, all these by default, A, B, C in are wires. By default, they are wires because I have nowhere declared, nowhere said these whether it's a wire or a reg. So now by default they represent wire. If you want them to be registered, you have to say output here reg. Okay. So because right now I am not done that because I am assigning with the combinatorial circuit. So combinatorial design. So that way I am not register. I don't need a register definition here because I'm not implementing register because it's combinatorial circuit. Output depends on inputs. Whatever A, B change, C in changing, and then just with the gate delay output, sum and C out will be given out. Okay. So further, these are ports, module name, port direction, and then this is the actual hardware. Okay. And you can also, same example, input and output you can give within the port itself. You don't want to give explicitly this one. Other way of doing this also possible. Have you observed the change here? Right? This is also other way of doing. Normally what will happen, because the port list will be huge, that's where we don't want to get into this one, and input and outputs here in an order we can give so that later readability will be easier for me in order to relay. Okay. Now, module name, you can have two things. One is the port, what I showed. Other one, parameters also you can have. Okay, parameters. Port direction, data type, right? And you can give range, port name, all these are possible. Now, parameters, right now, just hold on. When I come to the parameter topic, I'll talk. Right now, you assume that some named constants can be passed to the module. Okay, named constants can be passed to the module so that anytime when module is instantiated, I can pass a different value. For example, now this address I can control using parameter, either a 32-bit address or 16-bit address. Okay, and that is how I can control using parameter. And this is the width you can give. Same parameter is a constant. At the same time, tick define is also a constant. Okay, tick define is also a constant. Let us say tick define word is equal to 16, right? If you say, now you will have to use tick word here. Okay, if it is this, use tick word. If it is parameter, directly use this. Anyway, we will see more of it. So these are the different ways how you can declare the inputs and the outputs. So now, this is the dimension, right? Dimension, more than 1 bit, you can represent like this. And you can have input, output, in out. Okay, in out is bidirectional. Okay. So by convention, usually practice of putting output first, later inputs, not so mandatory. Okay. So simple D flip-flop example, if you take Q, D, Q is output, D is input, reset and clock are inputs, and these are the ports. Here you are seeing output reg Q. Output reg Q, because why I have mentioned reg here is I have to assign this Q, right, within base block. Okay, so input D and reset and this one. So you can give clock and reset, and then same way if reset is equal to 0 and Q int, and then Q is 0. Okay, and then Q int is D and Q is Q int. So that's where the output I am passing to Q. So that way I am mentioning this as. So actual circuits and all we will see, but this is the way how we can write this. Now this is the sensitivity list. Whenever any change at the passage of the clock or neck edge of the reset is when it enters. So if you look at the circuit, what this code will generate is this. Q is one flip-flop, Q int is other flip-flop. Okay, so you'll understand this specific thing, non-blocking, in the next couple of slides. I will explain. That is what has made this circuit, this code to implement two flip-flops. So Q int is intermediate flip-flop here. Q int is intermediate, where it is taking D input. Okay, now D is passed. Sorry, sir. This is D. Okay, this D is passed Q int, and then this is to Q, and this Q int input to Q. So this is in fact double synchronizer code. You will see all those. There are a lot of concepts more than the very constructs which you need to understand. Right, better learning of Verilog. So that's about the ports. Next, you have nets, one category. You have variables, other category, reg, integer, time, and real. Now nets, right? This try 0, wired and, supply 0, supply 1, wired or, try wire, try 1, try reg, try and. So basically we use more of this wire. Okay, so rest all we will use either in primitives or the structural modeling is where you use other things, like you saw in the structural or gate level modeling, you use most of it, but otherwise in the behavioral data flow model we use more of wire. Okay, variables, reg, integer, time, real. So now this reg and integer are synthesizable, time and real. Time is not synthesizable, real is synthesizable. So now other data types, parameter, genvar, spec, param, and event. Okay. So nets are physical connections between the devices. Okay. They have limitations. Whenever you declare these nets, right, they cannot be assigned in the initial or always block. So these are initial and always block are procedural constructs, we call procedural. Okay. Now declaring a net, wire, Range means how many wires, and the name. Okay. Now range is specified as MSB colon LSB. Default is 1 bit wide. When you don't give any range, it is 1. Supply 0 for ground connection. Supply 1 is for VDD. Tri-0, Tri-1 are used for tri-state devices, like tri-state inverters and buffers, like the Z, what I told, right? And wire type of net most used in the design must be continuously driven by something, cannot store a value. What is the use of wire? Just a connection. It doesn't store any value. What you drive, it just passes. They are assigned values using continuous assignment statements. A wire can drive a reg in the RHS of the procedural block. What does it mean? A wire can be connected as input to a register. Now you saw the flip-flop. Flip-flop input can be the wire, but output is of type reg. A wire can only infer to combinatorial circuits or combinational circuits. Wire can be bits, vectors, and arrays. Like this, you can define a range. So it's just that, okay, how many wires you want? Is 1 bit or bundle of wires? Like that. Bundle of wires, like a bus. Let us say this is 5 down to 0, right? There are some 6 wires you can represent. So now you may want to connect these 6 wires here, and then from this to this, right? This is where this is wire. And if you say these wires are connected to the 6 flip-flops here, and these are reg. These outputs of these flip-flops, this is reg. Again, these are wires. Like how to define wire A, simple wire. This is 6-state bus. Tri-state bus is, you saw, right, enable or disable, right? The input to the output, whether you want to tri-state, whether you want. So typically, right, tri-state means input, output. When it is enable, pass the input to the output. When it is disabled, what it has to do, this path is cut off. Now, you will have to drive some value here, right? And then typically, this is tri-state, you will drive Z. That is about the tri-state. So this is to store some small charge. They use this different, this one, okay? So more in primitives. 2-dimensional array of 8-bit wires, right? So these are 8-bit wires, and this is 2-dimensional array. So we'll see more of it. So nets are declared inside the module. Okay, Verilog nets and registers hold 4 value data. What are the 4 values? Now you are familiar. 0, 1, Z, and X. So now Z is output of an undriven tri-state driver, right? Undriven. Just now I explained, when it is disabled, it is the output of Z is the output of a undriven tri-state driver. And models, the case where nothing is setting a wires value. So when simulators cannot decide a particular value X, that is unknown, right? You have registers, right? Until you drive, you don't know what is the output of a register, 0 or 1, right? That is it. When a wire is being driven to 0 and 1 simultaneously, for example, now you have this wire, and this is one flip-flop, this is one flip-flop. For some reason, this wire, this output of this flip-flop, output of this flip, you have connected. Now this will be X, because now this is also driving, this is also what basically you're driving this wire crazy, right? So it represents X. Now, wire for interconnecting, wired or further it's a ECL type, and wired and open collector resolution. This you know better. You know what is this ECL? What is this open collector resolution? Right, constant logic 0, logic 1, pulls down when tri-stated, pulls up when tri-stated. Right, same as wired or wired and holds last value when tri-stated. Capacitance strength tri read small, and so this word and wired or this representation, right? So this is basic representation about all the nets actually, all the nets, but 99% of the time we will be this. Assignment is continuously evaluated. Assign statement are used inside module, not in procedural block like initial and always. Assign corresponds to a connection or a simple component with the described function. Target is never a reg variable. What it means, I'll show you with example. Now, assign, you cannot assign to a reg variable using assign. So now you have declared all these as wires. Okay. Now, these wires is equal to X. You can put an expression. You can directly take these values and then assign to these 4 bits. This is 4 tick B. We give these bits like this. 4 bit, right? This is because 4 bit, no, left hand side. So 4 tick B. You can say this is 16 tick H. This B is binary. This is okay. H is for hexadecimal, D is for decimal. That's where 0FF. So what it means, 16-bit H00. This 0 itself is having how many bits? 4 bits. 0, 0, 0, 0. FF 1, 1, 1, 1, 1. Like that, you see 16 bits. Now, another way of assigning is #3. You have seen an example. After 3 time units, what it has to do? Assign hand side to left hand side. What is right hand side? A plus B plus N, that is a 2 variables addition along with carry. These are 4 bits. And now these 4 bits, lower 4 bits will be sum, and whatever comes out, if it is carry, is C out. Okay. And this you have concatenated. Okay. You are concatenating C out and yes, the sum and the carry. So this is how, these are the different ways how you can use assign. Now, all that I am saying, target is never reg variable. Target means this left hand side is the target. Target is left hand side. It cannot be, if I say wire BS, wire C, sorry, C, that's wrong. Okay. So that is about the assign statement. You can put an expression like this on the right hand side. I've already shown one expression, the ternary operator multiplexer implementation on the right hand side. Now that's about the nets and the assign. And now comes to variable, reg, integer, time, real. These are the ones. Array can be declared. So we use more of reg. What is the story about reg? Is implicit storage, right? It stores, holds the value, okay, until a new value is assigned. How long it stores? Until you override with some other value, right? Used to model latches, flip-flops, but do not correspond exactly what it means now. The difference between latches and the flip-flops, right? And used in procedural blocks like always and initial. Register type is denoted by reg. Can drive a wire or as RHS of an assign statement. For example, now reg can drive a wire, reg output. Now this is wire, it can drive. Now to declare reg, what is the range, bit range, and the reg name? Reg can be bits, vectors, arrays. Is inside the module. So now integer is a 32-bit. Now reg anyway you will give the size. Time is an unsigned 64-bit variable. Real is double precision floating point variable. Real time is same as real. Okay. So the default value of where is z, right? Default value when you don't assign. Default value of reg x when you don't assign. So variable examples I am giving where reg. This is 12-bit scalar. This is 4-bit register. This is 32-bit memory. Each location is having 32-bit memory having 64 locations. So this is 64 rows, each having 30, each having 32 bits. So this one. Okay. So this is 0 to 63, 64 location. Sorry for my drawing. Yeah, at times you may not like it. I'm not good at drawing. So that's about the memory. And now this one, a 2D array rows and columns. These rows and columns, and each location having this 8 bits. So integer, you can declare this is array of integers. Okay. So now array of 1024, each having 1 bit, 1 location. So R1, R2, real also. So all how you can use these variable data types I have shown, and some of these we will execute these programs in the afternoon. So right now, just understand all that I have written is Verilog module. I have declared various wires, reg, integer, and I'm printing for you to show you right how when what values it has taken, how it displays, right, how it writes, all this. So this line by line program when we are explaining in the tool, we will walk through a line and we will explain. You can easily follow initial, begin and end. We have written line by line and displayed all values what assigned here, and further assigning and then updating those values. So this specific thing I have already touched upon, where number, size, tick, radix, that is binary or decimal or decimal, which you can use B, octal also you can use this one, and consecutive characters like this, 2 tick B, binary 2 is 1 0, this is 2-bit, and then AX, 8 tick H, this is, you can even assign like this, and then 12 tick octal, right, you can give this. So whatever explained, you can use some examples are given. They're very basic. Let us not spend too much time here. Okay, so the ternary operator, bitwise operator, right? Bit by bit, it will either complement or and, right? That's what it does here. Bitwise exclusive or yeah. Maybe this one specific concept I will explain, and then I'll maybe we can break for the next session. So Verilog introduces the concept of blocking and non-blocking, especially in order to clearly model the combinatorial circuits and the sequential circuits. Okay, So now that specific thing is done using different operators that on the non-blocking operator or blocking assignment and non-blocking assignment, and interchanging give a different circuit altogether, right? All those things we will see. So two forms of procedural assignment: blocking and non-blocking. Blocking we use equals, non-blocking we use less than equals. Now blocking assignment statement acts much like in traditional programming languages. What it means in traditional programming languages, whenever you are assigning any variable value to a variable, you do a print, you get the value what you have assigned, right? That is immediate assignments are done the blocking. Blocking means what? Until that completes, can go further, right? So then that statement should get executed, right? The whole statement is done before the control passes to the next statement. For combinatorial logic circuit modeling, right now it is understandable. What is combinatorial circuit? Output depends on the present inputs, right? And then based on that you evaluate and then pass it on to the output. So then that's where we use blocking assignments. Non-blocking evaluates all the right hand sides of the current time unit for the current time unit, and it assigns to the left hand sides at the end of the time unit. Okay, used for sequential logic circuit modeling. So what it means, whenever you are using this one, I'll explain with an example. The right hand side is evaluated fully, but assignment to the left hand side happens at the end of the time unit. At the end of the time unit. What is that? A little bit more we'll understand. So this declared register ABC 8-bit. Typical interview questions. What is the difference between blocking and non-blocking? Look at three variables. This is blocking. A is equal to 3, A is equal to A plus 1. Now, what is the value of A after the execution of this statement? A is equal to 3. Now, A is equal to A plus 1. Now, what is the value after executing this statement? A is 4. Now, I go for B. B is equal to A plus 1. What is B? Now, A was 4. Now, 4 plus 1 at this point in time, what is the value of B? It is 5. Now, when you display, now again, there is one more to comment here. Display prints immediate values, whatever available for these variables. Now, I use A and B variables. I am putting a format percentage hexadecimal format is what I am using, and I am printing A and B here, blocking. Now, what are the values of A and B? Maybe you can post in your chat in your chat box so that I'll also see some interaction there. What is the value of A and B which is printed here with this display statement? A is 4, 5. Okay. Now, A is, now what I am doing, A I am taking 3, B is 0. I am using non-blocking. A assignment is happening A plus 1. So I'm using non-blocking assignment. Now at the end of this, what is the value of A? A is 3. This is blocking. Now 3 plus 1, it is evaluated is the result which is evaluated, that RHS is evaluated, but when I in this at the end of this line, if you check the value of A, this will be 3 only. Okay. Now next, B is non-blocking A plus 1. Now what is A here? A is now 3 plus 1, B is 4. Now when you print this non-blocking A, B, you get now A is 3, B is 4. Okay, so now hope you are understanding clearly, because this is one important thing you should understand right throughout Verilog, as long as you are using Verilog actually. So that's why I'm spending time. And then okay, so now when you print, this is 3 and 4. Now until here it is the same time unit. Okay, now I'm moving to the next time unit, and I didn't do anything. I just displayed end of time unit as A and B. Now at this time, now I said right hand side was evaluated and not assigned, right? That is 4. And then here also it is evaluated. A plus 1, 4 plus 1, 5 was evaluated. But when I printed, it was printing 3 and 4. Now when it moved to the next time unit, when I print the same variables, it should get 4 and 5. Okay, this is non-blocking. If you look at this blocking, right? So basically, yeah. So I'll tell you this here. This is A plus 1. This is not 5. This is A was 3, right? This 3 plus 1, 4. Okay, so not 5. So B is equal to A plus 1, right? Right, and then 3 plus 1, 4. So now blocking 4, 5, my explanation, 4, 5 printed, and now non-blocking 3 and 0. What will be printed? A is 3 initially, and B is 0. These have resulted in updation of left hand side. Okay, and now after this time unit, you see A is equal to 4, right? A is equal to 4 because A is equal to A plus 1, that is 3 plus 1. Okay. And then if you look at B is equal to A plus 1. So this specific, this one is, that is 3 plus 1, which is this is about blocking, non-blocking. So this program will execute in the afternoon, and then any further questions we will take afternoon session. So we will take a pause, and so most probably because we will demonstrate some examples, and then we will
Shivappa, I think you're not audible. Hello?
Hello.
Yeah, came back. I think we are not audible in it.
No, sir is not audible. Speaker.
Okay. Step number one, already we have written that step number one will be make all the rows.
Hello? Hello?
One of those bits.
Uh, 1 minute. Can you hear me now?
Yeah. Go ahead.
Yeah. So what I was telling is, afternoon, I think the program of it is designed is afternoon is all lab, and because there are other constructs which we need to revisit here, the theory part. So we will demonstrate all the things and certain examples, and then we will revisit for the theory part. We will do hand in hand both theory and then the demonstration of the lab examples is what I was mentioned. Is that okay?
Yeah. For today, we can do like that because that was the plan. But
Yeah.
is it possible? Just I am wondering, is it possible that tomorrow we do like a theory you explain and go on doing hands-on also parallelly? Is it possible?
No, that's what I'm saying. Right now, introduction has been given. Now certain programs have been discussed. We will execute those in the afternoon, and maybe that might take close to 1 hour. Again, we will revisit the theory part, and then further functions, tasks, all this we will talk, and then we will take them to the lab. Only thing is, now during our session, they may not get time to do the lab. Just they will be, audience observing, but only in their respective time slots after these 2 days or in the evening after our class hours, they can experiment their programs.
Yeah. No, but what I was thinking is like tomorrow, today you go ahead with your plan, but tomorrow I was thinking you are explaining a concept and immediately showing some demo like that parallelly, rather than separating theory and practical. Can we have?
Maybe pretty much, we will do like that. So what we have done is little bit more of theory in the afternoon. Morning. We have pushed
Okay.
that. Otherwise, otherwise, normally this is how we do the course. Where, for example, now blocking, non-blocking, we execute that program.
It's good. Sure. But it's good, na? Directly, if you show it in a program, what is blocking and what is non-blocking, it will be good. Okay. Anyways, so we'll take break now.
2 o'clock.
2 o'clock. 2 o'clock. We will resume at 2 o'clock. So same link. All of you can join. I'll stop the meeting. We can resume at 2 o'clock. Okay.
Yeah. Okay. Thanks a lot.
Thank you. Thanks. Bye.
Okay, so this comes out to be E actually.
राठौड़ सर,
हाँ
सर एक रिक्वेस्ट है, जो
बोलो
मॉर्निंग
ना।
टेस्ट का टाइमिंग है ना सर, वो
हाँ,
थोड़ा 10 की बजाय 10:30 तक हो सकता है क्या?
अच्छा ठीक है सर।
सर, वी आर हैविंग द लेक्चर्स फ्रॉम 8 to 10. आज सवेरे
अच्छा
मैंने
ठीक है।
मैंने ट्राई किया उसको, बट तब तक वो
अच्छा
लॉक हो चुका था.
ओह
And
ठीक
we
है, कोई
got
बात नहीं।
permissions only with so we should not miss the lecture. तो
मैं अर्ली मॉर्निंग चालू करूँ 7 o'clock ऐसा जल्दी 15-20 मिनट की टेस्ट नॉर्मली सर सिंपल 10 क्वेश्चंस रखते हैं।
नहीं सर, प्रॉब्लम वो नहीं है. 8 बजे हमें कॉलेज में आके लेक्चर ये करना पड़ता है, तो 7:30 को हम घर
अच्छा।
लेट कर देते हैं. तो मॉर्निंग में बहुत लेकिन, तो आप 8 बजे से लेके उसको 10:30 तक कर दीजिए. दैट विल बी फाइन. मिस
अच्छा
अदर
ठीक
पीपल
है।
डोंट हैव प्रॉब्लम. बाकी कुछ नहीं.
ठीक है चलेगा, कर देंगे गाइस।
यस सर, थैंक यू.
ओके।